Welcome to this second lecture video for Physics 4A. In the set of lectures in this video, we will introduce the vocabulary and the tools we use to help us analyze motion of objects. We will start with the statement of the definitions and some careful distinction of the two terms, velocity and acceleration, and our intuition associated with these terms. Then we will introduce the motion graphs and illustrate their use with a couple examples. We will take some time to derive the kinematics equations that we will use in problem solving for situations involving constant acceleration. And we will wrap up with examples of free fall, which in fact provides some of the most common real-life situations involving constant acceleration. Everything you will see in the following lecture videos are applications of these definitions. Given the position of an object as a function of time, x of t, the velocity of the object is the rate of change of position, which we calculate as a derivative of x with respect to t. And the acceleration of the object is the rate of change of velocity, or a derivative of v with respect to t, or in terms of x of t, the second derivative of x with respect to t. This is the key definition you will see used when we interpret motion graphs and when we derive the motion equations for the motion under a constant acceleration. Their importance cannot be overstated, and I recommend that you memorize these boxed relationships. It'll help you follow the applications in the lecture videos in this set. Average, velocity, and acceleration are similarly defined, except instead of derivatives involving infinitesimally small dt, we use a finitely small delta t. In many circumstances where delta t is small and we are okay with approximations, we will use average velocity interchangeably with the instantaneous velocity. But sometimes, we are interested in an average velocity for a time duration involving a pretty large delta t. In that case, we should remember these boxed definitions and remember also that average velocity is not the same as instantaneous velocity. Unless we emphasize this difference in a given context, you can safely assume that by velocity, we mean instantaneous velocity. In my experience in teaching physics, most people have a great intuition for velocity. If I tell you that a car is moving at a speed of 60 miles per hour in a direction to the east, for example, then you know intuitively what that's like. You even know what it feels like. That's what I mean. A lot of people have great intuition for velocity. It's acceleration we have to distinguish more carefully from velocity. So let's start with the definition. So acceleration is defined as the rate of change of velocity, or using symbols to express the same idea more succinctly, we would say acceleration is equal to how much velocity changes in a given amount of time. And if we are being picky, we need to be careful about velocity being a vector. It has direction. So acceleration is also a vector. It has direction. So the definition is all well and good. The problem here is that a lot of physics students initially don't have a good intuition for acceleration. So you can memorize this definition, but it takes some time for you to internalize this definition. And here's why this distinction is important. Velocity and acceleration are how we describe motion. But when we say motion, the idea of motion is quite not precise enough. One thing you can see is that both the velocity and acceleration are somehow involved in motion. What we now have to carefully separate is different parts of motion that you have a instinctive, intuitive connection to, and how those different parts are related to acceleration and velocity. I think here's one useful statement to make. Acceleration is how you feel motion. We'll see that in a little bit in more concrete examples. All right, let's start out with some examples. I think it'll be useful to start out with an example where there is motion, but you don't quite feel it. A good example of that is an airplane ride. Or if you've never been on an airplane, you can imagine a BART or subway ride. So imagine you are in an airplane. You know that the airplane is moving very fast. A lot of commercial airplanes will be flying at something like, let me make up a number that is pretty close, 700 miles per hour. But one of the strangest thing about airplane ride is that you don't really feel that. Now, if you haven't been on an airplane, then I want you to imagine that you've been on a BART ride. Now, BART doesn't move as fast as airplane. Maybe it moves at, I don't know, 70 miles per hour. Now, maybe you have been on BART and you don't feel like you didn't feel the motion. So this is where I want you to start making this distinction. Imagine the part of the BART ride as the train is moving at a constant speed. It just left the station, it reached the maximum speed of 70 miles per hour, and the next station is a few minutes away, so it's continuing to move at 70 miles per hour. It's that portion of the motion that you don't quite feel it. You only feel that BART is moving when it's beginning to move or when it's coming to a stop. So this is an example of motion where acceleration is 0 and the velocity is not 0. This is what I mean. Acceleration is mostly what you feel in a motion. All right, let me move on to second example where you feel a lot of motion. I guess not many people would have this direct experience, but you can use your imagination. Imagine a car chase. Or you can imagine that you are riding with a particularly aggressive driver who's speeding and changing lanes. Let's say as this car's being chased or chasing, it's weaving in and out of traffic, changing lanes a lot. Then you can imagine what that feels like. You will be jolted back and forth in the car. As it speeds up and slows, you'll be pushed back, pulled forward. You've been in a car, you know what that feels like. Well, maybe not exactly what a chase feels like. You know what the milder version of that feels like. So this is the case where velocity is not 0 because car is moving, and the acceleration is not 0 either because the velocity is constantly changing, and acceleration is given by change of velocity. So as the velocity of the car changes, you have this non-zero acceleration. So for example, at this point, the car had a velocity like this, and at this point, car has a velocity like this. At this point, car has velocity like this. So you can see that even if the car was moving at the same speed, because the direction of its motion is changing, its velocity is changing, and that change of velocity will be associated with an acceleration. And actually, this is a lot closer to our everyday experience. And I think this is why in our intuition, how we feel motion and which part of the parameter, velocity or acceleration, is responsible, it's mixed up because in most of our everyday experience, it's all mixed up. So intuitively, we don't quite know whether to credit the velocity to our sensation of motion or credit acceleration for our sensation of motion. Now, I don't know how many of you have been to Universal Studio, or I guess there could be other theme parks that do this. There are machines called motion simulators. And what the motion simulator simulates is the acceleration. You can kind of see that from outside. When you look at the motion simulator from outside, its velocity is more or less zero. It's not going anywhere, but it's jerking back and forth and it's tilting. So it's causing acceleration for people inside. And if you're sitting inside, you are looking at the screen, some video that's consistent with the motion you're supposed to be feeling, and it's a very realistic feeling. It's because our sensation of motion is based on acceleration. So I hope this example is helping you realize that when you are feeling motion, what you should look out for is acceleration, not velocity. But it is a fact that so much of our intuition about motion is tied in with velocity. We feel like if something is not moving, velocity zero, that there's no motion happening. So I want to end with the last example where there is no motion in the sense that velocity is zero, but there is acceleration. To crystallize that you can have acceleration with zero velocity. And even though you would be feeling motion at that particular moment in time, the velocity is zero. So I don't really have a good name for this, so let me just call it non-zero acceleration with zero velocity. So imagine you are in a car which is stopped at a signal light. The light is red, so the car's not moving. Its velocity is zero. And since it remains at zero, its acceleration is also zero. You don't feel like it's moving. Now, at time equals zero, the light changes from red to green. And the car starts to move forward. And you feel this motion. If you step on the accelerator, the pedal hard enough, you will feel thrown backward in the car. That's how you're feeling the motion. Now, this is the question I want you to consider. At time equals zero, when the light just turned green, what is the velocity of the car? Now, it's tempting to say that the velocity of the car is also greater than zero. After all, isn't it moving forward? But what you have to carefully consider is that we are looking at time equals zero. This is the moment at which light turned from red to green. Now, let me do a little bit of math here. I can take this definition here and turn it into a statement about the change of velocity. So the change of velocity is acceleration times duration of time. So before time equals zero, your acceleration was zero. So no matter how long you wait, change in velocity would have been zero. Now at time equals zero, the duration of time over which acceleration was that zero has been zero. That's the exact moment at which acceleration flipped from being zero to non-zero. So what that means is there haven't been enough time for the velocity to have changed. So at time equals zero, velocity still is zero. So this is the first very common everyday experience where you feel the motion, you have non-zero acceleration, but you have zero velocity. Now, what you should notice is that this moment is very fleeting. Another moment, a second, fraction of a second later, your velocity won't be zero. Because with non-zero acceleration, as you accumulate change of time, you will accumulate change in velocity. So all these examples will be very momentary, fleeting. Now, let me give you one more example of non-zero acceleration with zero velocity. I have this ball here. When I throw it up and catch it, at the very top of the motion is another example of where it has non-zero acceleration with zero velocity. So let's say at the bottom, I threw it up with a velocity of 5 meters per second. Then about half a second later, at the top, the ball would have a velocity of zero. And then another half a second later, the ball will have come down and it'll be moving downward at 5 meters per second. And this is the rough trajectory of this ball. So at that exact moment, when the ball is at the top, its velocity is 0. I can say that its velocity is 0 without actually measuring it from this argument. If it had positive velocity, it would be moving upward more. If it had negative velocity, it would be moving downward. So by the fact that it's at the very top, its velocity has to be 0 because it's neither moving upward nor downward. And I'm saying that this is an example where acceleration is not 0. Now, how do I know that acceleration is not 0 at the top? Maybe it's 0, like velocity was 0. Well, here's how I can argue that the acceleration at the very top is not 0, even though velocity is 0. It's because of the change of velocity. The moment before it reached the top, the ball was moving upward, so it had a positive velocity. And the moment after reaching the top, the ball will be moving downward, so it has a negative velocity. So because of that continuous change in velocity, I know even at the very top, the velocity is still changing. And because this velocity is changing, that means acceleration is not 0 at the top. So these are some examples distinguishing between acceleration and velocity. And I hope this is giving you enough concrete examples for you to be able to distinguish between these two things, acceleration and velocity, in your own thinking. I will tell you that this is a simple concept once you get it. But until you understand, because there's so much your natural intuition working against this correct distinction, that it'll take effort for you to get it. So I have 3 axes to draw position, velocity, and acceleration for different scenarios. So I wanted to just to talk about some of those scenarios um, and represent those scenarios in terms of motion graphs. So I guess we have maybe about 10 more minutes on this. So let me do one that kind of relates to one of the questions, homework questions you have. But I realized in the homework question, it's kind of cut a little bit short. So I will extend that a little bit to illustrate that with with a situation where you might have to describe some situation with multiple stages. So the homework question I'm thinking of, it has a scenario with a diver diving from uh, 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 diving board. I think I'm saying diving too many times, but it's okay. Um, so the situation will describe it. A diver jumps straight upward from a diving board with some speed v naught, um, and on the way down she barely misses the diving board and um, dives straight into the pool. And I think your homework question ends here, but let me add a little bit more bit so that I have more interesting motion graph to sketch into the pool. And after entering the water, she slows down with an acceleration. Let me make up some number of a equals 5g. That seems a lot. A equals 3g. Or that would be approximately 30 meter per second squared. Um, so that's the scenario, and I want you to uh, want you to show you how you would sketch something like that on a motion graph if you had to. Now, on your homework question, you don't have to because there's no real good way for my method to grade that. So you won't have to worry about doing this on your homework, but it's something that you should know how to do. So now, one thing I will start by saying is something like this is very difficult to sketch on position graph correctly at a first try because your intuition kind of messes you up. So let me give you some attempt, and then I will use the velocity and acceleration graphs to kind of um, kind of make some of the more ambiguous things clearer. So let me draw a kind of reference line for the water level so that at least I know when the diver enters the water or not. So wait, is that the yeah, water level? Actually, I guess I need to draw two different levels. So let me do one for water level and one for the so let me draw two levels. There's one level for the water level, and I think I need a second level for the where the diving board is. So let's say the diving board is around here. Then on a position graph, you might draw something that looks like this. The diver starts from the position of the diving board at time equals 0. And maybe you remember enough of projectile motion or motion with a constant acceleration that you know to draw something that looks like a parabola. So this is with acceleration being downward acceleration of minus g. And then what's a little bit harder to do on a position graph is what happens to the position after the diver enters the water. You have some sense that the diver should come to a stop because it's something about slowing down. And that's kind of where you have to leave it. And this graph, as drawn, it's ambiguous. It's not wrong, but there are some features here that's not best represented on a position graph. So let me do that on an acceleration graph instead. So on an acceleration graph, I can translate the physical situation described in this statement a lot more faithfully because I can take a point that represents when the diver enters water. And that's a very clear dividing line for acceleration. So before the diver enters water, I know that the acceleration of the diver should be minus g. So this is minus g. And while the diver is in the air, the entire time, the acceleration is minus g. That's what free fall, motion under gravity alone is. And when the diver enters water, then the acceleration changes. And this is where you kind of have to think through carefully whether it should be minus 3g or it should be plus 3g. This is where you want to think in terms of relative directions. The diver, at the moment when she enters water, she's moving downward. So in order for her to slow down, the acceleration must be upward. And you can kind of see that represented here in the upward curving position curve. And it's in this acceleration graph that you would make that clear that after diver enters water, she undergoes an upward acceleration of plus 3g. So yeah, on the acceleration graph, and this is where I should stop. And on the acceleration graph, this is more or less one-to-one faithful representation of what the questions take, what the word description described. And for that reason, when I usually draw a motion graph, it's the acceleration graph that I usually want to start out with. So, okay, once you have acceleration graph, then you have enough information to start drawing velocity graph. And this is where you have to put on your analytical hat and really think through this mathematically. I know it all looks like a picture, so that's where people sometimes make a mistake of kind of going kind of going with your feelings. And until you develop your intuition for kinematics, you don't want to go with your feeling here. You want to actually read carefully from what the statement says, keep thinking about what you learned in calculus, and apply that here. So it said diver jumps straight upward with some speed v naught. So you are given an initial velocity, and you need to use that here. You cannot start the velocity from zero position or any random point you pick. There's a positive v naught that you start from, and it's positive because it's upward. And then so I like to think linearly, sequentially in time. So I know what the value of velocity at time equals zero. So the next question is, how is the velocity going to be changing as you move on from time equals zero? And the one guide you have is the acceleration, which is the derivative of velocity. So it's going to give you the slope of the velocity as you go from here. You have minus g, so that should be the slope, something downward sloping, negatively sloping. And I'm trying to kind of put the negative slope in a way so that it'll make my graph kind of to scale for the next part. So let me do that, and until I reach this point in time, when the diver enters water, it's going to be this one constant slope the entire time. So the graph will look something like this. And so this point is a special point that you couldn't see in the acceleration curve. It doesn't look special in the acceleration curve, but it's this special point in the position curve. It's the point where the diver was at the top of her motion. So that should match up in your position curve, where you do see now that the slope of the position curve is zero, and the value of velocity is zero there. And at the moment where diver enters water, something happens, and that something is that the slope of this curve now changes to positive 3g. So it's going to go from being negatively sloped, downward sloped, to upward sloped, positively sloped, and it should be steeper than this because because now it's 3g. So let me just put this point here so that I can do it reasonably to scale. So it looks something like this. So once again, constant slope, and this should the slope here should match up with the value you see here. The slope that you see here should match with the value that you see here. So and once you draw this correctly, then you can see that how I drew the position curve here matches up. I started out with some steep negative slope, and it flattens out to a zero value or zero flat slope, and that matches with the velocity going to zero. So that's an illustration of drawing a motion graph. Okay, let me do one fun one. So I guess I had a bunch of scenarios. I don't have time for all those scenarios. So let me just do one, what I'm going to claim is a fun one. So this diver thing, it's good for illustrating how you go about drawing the motion graphs for a very clinical kind of physics problem type question. But it's not, for most of us, it's not very relevant to what you might see every day. So I wanted to illustrate a motion graph for what you might call stop and go traffic motion. That might be something that people see more regularly, like if you're driving in a congested city traffic, you are able to move for a bit, then you have to stop, move for a bit, and then stop, move for a bit, and then stop. So, so I hope that description is clear enough to people. So motion of a car in a congested traffic condition. So let me do that. And this is actually a bit of it's kind of opposite of the scenario I just drew. It's actually easier to draw with a position graph because I think you can intuitively get what that motion should look like. So let's say time equals 0, you start up from position 0. So you start by moving and then you stop for a while and then you are able to go again. So you start moving again and then you stop for a while and then you are able to move again and then stop for a while, able to move again, stop for a while, and so on. It looks like this. And I could have drawn it more prettily, but that's a kind of, and intuitively that accurately describes what a stop and go traffic looks like. And once you have that, then what I want to do is draw what the velocity and the acceleration curve looks like. There are some idealizations I'm making here. So for these segments of motion here, I'm going to assume that it's moving at a constant velocity. In real life, it might not be, but I'm just getting, I guess, the average velocity and approximating that to be the instantaneous velocity for the entire time, even though it probably isn't. So let me get a few time marks here. So I will get those into the velocity curve so that I plan out my time axis correctly and I don't run out of any space as I'm drawing them. So I have, it probably works out best if I number them. 1, 2, 3, 4, 5, 6, 7, 8, 9. I shouldn't have done so many. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I'll probably need that for acceleration too. So let me do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So so the time period is broken up into basically 9 or 10 periods, depending on how you count. And I'm just gonna sketch out what velocity and acceleration looks like at those different times. So from 0 to 1, I have constant positive velocity. So this is the velocity from 0 to 1. And then I have constant but 0 velocity. So that's 1 to 2. And then I have constant velocity, which I guess I drew it faster than the first one for some reason. And then it's 0 again. And then it's some positive constant value. And then it's 0, 5 to 6. And then 6 to 7, it's some positive value again. 7 to 8, it's 0 again. And 8 to 9, it's some positive value again. And then 9 to, it's 0 again. It looks very disjointed. And it's part of the approximation that I'm making, because I'm making this approximation that velocity is suddenly changing from one value to 0. And within that approximation, the velocity looks disjointed. If you want that to look more real, you could connect them, and that looks more physically meaningful. It looks like a more physically meaningful velocity curve, but it's a part of making that approximation of that there's a sudden changes. And you will see that approximation bleed through in the acceleration curve as I draw it now. So in the acceleration, when I draw the acceleration curve, it's almost better ignoring the position curve altogether, because really the relationship that's most useful in giving you the intuition for acceleration is that it's a derivative of the velocity, meaning it's represented by slope of the velocity curve as a function of time. And sometimes that'll make us draw something that initially doesn't look intuitively correct, but well, that is what's actually mathematically correct. So from 0 to 1, where the car is moving with a constant velocity, the acceleration is 0. And a lot of people might have difficulty with this initially because it's moving. Why is acceleration 0? Well, the slope here is flat. Velocity isn't changing. Now, to get to this positive velocity, you probably had a non-zero acceleration before, but during this period, 0 to 1, acceleration is 0. And I guess maybe let me do this all the segments right now and get it out of the way. You see that for all the segments between 1 to 2, 2 to 3, 3 to 4, they are all flat. That's a part of the approximation I made. So acceleration during all these periods within this approximation is all 0 between these transitions. So that's the part that, oops, it's meant to be 0. That's the part that's going to be look very unintuitive to people who haven't thought about this way before. That for vast majority of the time, acceleration is 0 because you have constant velocity. Whether it's at a constant non-zero value or whether it's at 0 value, it's constant, so acceleration is 0 during those times. What gives you all this interesting motion in the end is what happens at a very small moment of time. So over this very small duration of time, you have a highly negative acceleration. So I have a spike in acceleration in the negative direction here. I have a spike in the acceleration in the positive direction here. So this acceleration curve is very poorly behaved, which is why it's not a good one for practicing how you draw the motion graphs. But basically, these very steep slopes are what gives you these pulses in acceleration. Positive pulse, negative pulse, positive pulse, and negative pulse. And it looks very it doesn't look correct according to intuition of many people starting out, but this is what the math says it is. And part of your experience with learning kinematics, the way we cover actually in calculus and in physics, is developing this intuition that this very oddly looking graph, which you might not have expected, is actually correct. And if you have experience driving, it kind of does match up with your driving experience, hopefully. Well, at least the very bad driver. When the car comes to a stop, you weren't planning, so you suddenly come to a stop, sudden braking, and then when the car in front of you starts get going, you suddenly accelerate, and then when it stops, you suddenly stop. I mean, it does represent a very bad driving. But if we are trying to draw a very good driving, then these position curves wouldn't look like a straight lines. They would look like a parabola, where acceleration is more gentle. In this video, we will derive kinematics equations. I want to start out with the motion graphs so that we can ground our discussion on some conceptual basis. Let me start out with the position graphs on the left, moving on to velocity and acceleration. And these are, of course, all functions of time. So a particular example of motion graph might look like this. Position. And I guess actually that's it. For me to now draw velocity and acceleration, I'm now constrained by what my position looks like. So if this expresses my position as a function of time, then I have to stick with the definition of velocity, which says that velocity is the time derivative of position. And for acceleration, I have to stick with the definition that says acceleration is the time derivative of velocity. And you might remember all this from your calculus class. So the derivative is graphically represented by the slope of the graph. So I find here where the slope is 0, horizontal, then that would be the point where velocity is 0. And I look to the right, I see that slope is getting more and more positive as time goes. So I plot out velocity that gets more and more positive. each moment in time. And to the left of that, or earlier time before when velocity was 0, the slope is negative, downward sloping. So I also plot out ever more downward sloping velocities to the left of that point where velocity is 0. And if the position curve is actually a parabola, then velocity curve looks like this, a straight line. So when you look at the velocity graph, you see that it has this constant upward slope. So it's a positive slope that has constant value at these different points in time. And that represents acceleration, the time derivative of velocity. So this is one of the first things you learn in calculus, and how to relate graphs of a function with its derivative. So hopefully this feels familiar enough. And now what I want to do is go the other way, backward. Starting from acceleration, I want to work out what is the velocity and what is the position. So instead of an ending point here, our starting point is going to be this, that the acceleration is at some constant value a naught. Let me move this axis around a little bit so that I can plot more easily going the other way. Alright, this is a little bit better. It's nice to think of your motion starting at when time equals 0 and working out what happens as time advances into the future. So we have constant acceleration, and what we want to do is we want to build out what the velocity and position will be based on the fact that we have constant acceleration and the definitions of velocity and position. So from your calculus class, you know that if your acceleration is related to the velocity through the derivative, then the reverse relationship is the antiderivative. That is, the velocity is the time integral of acceleration. But what does this mean? What the integral means is in one simple phrase, area under the curve. So if we are looking at velocity at these three different times, t1, t2, and t, then to find the velocity, we look at the area under the curve up to the time t1. And then we look at the area under the curve up to the time t2. And then later on at time t, we look at the area under the curve up to the time t. Now, I hope as you look at this that something doesn't quite fit it with what you saw at the beginning. Didn't our velocity start out negative? How does that fit with this description? That the velocity represents area under the curve. Area is always positive. So this is where I have to be careful. And this is the reason I want you to cover kinematics equation derivation the way I will cover it now. So it's a little sloppy to simply write that velocity is the integral of acceleration. How is it sloppy? Well, there are a few things that are left unspecified. In calculus class, you see them in terms of integration constant. The integration that you do on this side doesn't define function v uniquely. It defines it up to a constant, and then you have to put in the constant later. This is the idea I want to introduce. In physics, almost all the integration we do are done as definite integrals. So instead of leaving loose ends hanging, I am going to specify what my integration limits are. The integration with respect to time t, that's my x-axis here, it's going to go from t equals 0 to the final time is, oh, I need to make sure I don't use the same letter. Let me just call this t sub f, and I'll replace that with a t later on. And I hope that these limits will start to highlight and cause you to start thinking in terms of two endpoints, the initial and the final endpoint, which means there is some initial velocity that you should be thinking of, and there's some final velocity that you should be thinking of. So this equation here is sloppy because I wrote the left-hand side as simply v. What it really is change in v, or final velocity minus the initial velocity. Okay, let's finish this calculation and we can show the graphical interpretation above. Our acceleration a is constant, so the integral on the right hand side is simple. Here we do use the antiderivative to find the, well, integral. So the antiderivative of a constant function is the constant times the variable of integration. And this is the definite part of the definite integral. You evaluate it at the two limits, the upper limit, t final, and the lower limit, t equals 0. So plugging those limits in, you get a tf minus a times 0. This is the definite integral process you learned in your calculus class. And I want you to get into a habit of using this a lot more than you are used to using it in your calculus class. So we have this left-hand side here and this right-hand side here. Let's solve this for the final velocity. Then the final velocity is equal to v naught plus acceleration times the final time. And as in your textbook, by convention, we get rid of that f subscript. So this is one of the kinematics equations for velocity under constant acceleration. You start out at some initial velocity, and the acceleration changes the velocity as a linear function of time. And this shows where the negative value of velocity came from. The initial velocity was simply negative. So what that means is at time equals 0, we start out at some negative value of velocity. And what this area under the curve represents is the change in velocity. So from time equals 0 to time equals t1, the velocity changes by the amount of area here. So let me just scale it so that brings the velocity to 0. And in the additional time from t1 to t2, the velocity continues to change by amount of area here. So let me continue drawing straight line. And from t2 to the final time t, the velocity continues to change by the amount of this area here. So that's the velocity graph. And depending on what the initial value of the velocity is, now where it gets interesting and where I want you to put in the effort now to gain the conceptual understanding of is the next step, going from the velocity to position. So the velocity is the time derivative of position. So that means, sloppily stated like before, that position in some sense is the time integral of velocity. And we can go as far as to say that this is related to area under the curve. Now before, with the area under the constant function curve, that area was the same size for the same time interval. So you could see that the amount of change in the velocity that should undergo is the same amount That's where we got the linear function. Where we now have to be careful is that when you look at the area under the curve from T1 to T2, for example, that this amount of area is different from the area under the curve from T2 to T, this trapezoidal area. And if all you are interested in was answer, then we can work out the geometry, do base times height, divide by 2, sum of two bases times height, divide by 2. You know how to do the geometry. But I want you to use this as an example of picture of things to come. And this is how we are going to handle the question of area under the curve, where the curve is not constant. Here, the conceptual procedure is this. Instead of trying to take the entire large chunk of the interval, you have to think of dividing this interval into tiny little infinitesimal pieces. And the way the area under the curve is represented and calculated are the areas of these tiny little bars. So when you look at the area here, for example, what that area will be is the sum of the value of the function. So I guess here that's a v. That gives you the height at each of these points. I could call that v sub I times the size of the interval. Let's call that delta t. And we are adding up all these intervals. So I goes from 1 to n or something like that. Hopefully all this sounds somewhat familiar. This is something that you would have seen in Calculus 1, and they have a name for it. They call this Riemann sum. You have seen all this before, so why am I going through this painstaking description? I want you to file this away and keep this in mind as we talk about forces and rotational inertia later. This approach of taking a large interval that we don't know quite how to handle and breaking it into infinitesimal pieces, handling each infinitesimal piece, and then adding it all up together, which is most conceptually easily represented as a Riemann sum, and recognizing that when you take the limit of the size of the interval going to 0, that becomes this integral. That's going to become a very common and very familiar approach. So let's finish the derivation here. So to derive the position as a function of time, we do the same thing as before. So that's going to be integral of velocity as a function of time. This time it's not constant. And you integrate it over a definite interval from time equals 0 to some final time. And we can plug in the expression that we derived into this integrand, since we need an explicit form to actually do the integral. This is a polynomial integral. We know how to do it. The antiderivative is v0 times t plus, that's linear, so it's going to be 1/2 a t squared. That's the antiderivative. And to double check and make sure that you didn't make mistakes in your head, you should think of taking the derivative of this. When you do that, you get the power of the polynomial that comes down, cancels it with 1/2, so you get at back. Good. Let's plug in the limits for the definite integral. The time goes from 0 to the final time, t final. So that's equal to plugging in t final, v0 t final plus 1/2 a t final squared. And when I plug in 0, I'm gonna get 0 for both terms, so nothing. And don't forget, the left hand side isn't actually x when you do it this way. It's the change in x. So what it should be is x final minus x initial. Take this left hand side and this right hand side, solve it for x final, and for presentation, get rid of this final subscript. And that's the kinematics formula for the position as a function of time. And you can see that you get a parabola potentially with some offset along the x and y directions, or the horizontal, which is the t-axis, and the vertical, which is the x-axis. And in the graph that we studied out this derivation with, it looked something like this. But all this would depend on what is the initial velocity, initial position. But what I want you to observe and take away from this third derivation of kinematics equations is this use of definite integrals. You are going to be seeing this a lot, and I'll point this out again when we get to forces and rotational inertia, which are the other two topics where you're going to be using integration as a problem-solving technique more so than in other parts of this class. And I talked about free fall a little bit in a previous semester's session, and it's linked from the lecture, the chapter readings and lectures page, but I kind of hid it as this link rather than full-fledged embedded video, mainly because it's question two is to what? It's a little bit too short, and I so I didn't want to disrupt the flow of the page, and really all that this page, this video gets to is what is our almost mathematical definition of free fall. So when you look at section 3.5, we do define free fall, and I think I pointed out towards the end here. So the wait, let me go to the textbook. Textbook should give a definition of free fall, and it's a so as I say in the video, as much as I try to resist equating mathematicians with the physicists, because our approaches are different, there are some ways in which we physicists act like mathematicians, and how we handle free fall is one of them. We have a definition of free fall. The definition of free fall, which is that which describes the motion of an object falling in a gravitational field. I don't think that's quite sufficient. Let me find it here. So this is the definition of free fall. An object falling without air resistance or friction, or actually any other force, is defined to be in free fall. And in the way we define free fall, what's more important is not actually the fall part, because if you look up above, you will see that we define fall kind of weirdly. So the falling, it doesn't quite help you connect our definition of free fall to your intuition. Because falling in the context of free fall does not mean the body is moving from greater height to a lesser height. So what does falling mean? It's almost meaningless. When we describe free fall, what's more important is the free part. So object falling without air resistance or friction. And I guess in some sense what we mean by falling is that this object is not touching anything else. So so that's what free fall is meant to describe. And there's an aspect of it, this that's a bit stilted, it's awkward, it's confusing. And that's because we are trying to describe free fall without having all the tools to actually describe free fall. And the tools that we need to describe free fall, you really need the concept of force to have a clear distinction of what contexts you might describe it as free fall and what contexts it's not a free fall. Because really, the situations that you would describe as free fall are the situations where the only force, the only potential possible force on the object is gravitational force and no other force. So as you go through this week's material, you will see a lecture on types of force. So free fall is the circumstance where the only type of force you see being exerted um, on your body is gravitational force. So we describe all these different forces, and once you come to a conclusion that for a given situation that the only force acting is gravitational force, then great, you have a situation of free fall. And to help you with that intuitive feel, this page actually has some videos of examples of free fall. So this is one of them. Let me just skip ahead to the portion where it is in free fall. She's about to go into free fall. So when she comes off the floor of the airplane, she's in free fall. Now, in this particular perspective of the video, you can't really tell if she's moving up or down. At the beginning portion of this motion, actually, she's still moving up. It's in the portion where the airplane is doing the parabolic arc as they are moving up but accelerating downward. That's when all the passengers are beginning to be lifted up. That's that's the beginning of that free fall. But I'm highlighting this portion as free fall because you can tell because she's not touching anything else in the airplane, and you can kind of guess that the movement of air in the airplane is slow enough that air resistance is going to be negligible. This is free fall, where there's no other possible source of force on her other than gravity. And there's one other example of free fall on this page. It's linked here for reasons for this week, because this week is really focused on free fall. Astronauts on space station, they are in free fall. And you can see because other than when he's briefly touching the ground, let me just skip ahead. He's okay. Now he's not hooked into anything. He's just floating. That's when he is in free fall. So just before he pushes the other person, they are in free fall here. Both of them are in free fall. Well, together as a system, they are in free fall. So, so yeah, that's I think the full description of what it means for an object, person, or anything to be in free fall. And what's important there is the free part, because by free part we mean no forces. Other than possibly gravity. I guess that's the fall part. So, so yeah, so I think the in the last 2 weeks material, the best example of material that we cover under free fall is projectile motion. It's that motion of an object that's been launched with some velocity and then accelerating under the force of gravity only. So if we want to associate free fall with a projectile motion, that would be, I think that would be okay most of the time, like 99% of the time. There might be some counterexamples, but it'll be hard to find, or I'll have to think about it. So yeah, I think that covers the additional description of free fall, what situations that it covers and what situations it doesn't cover. I guess the most common mistake people make are not thinking something is free fall because the object is still moving up. Like if I don't have my if I throw this ball up, while it's moving up. Sometimes people think that's not free fall. Well, while it's moving up, if it's only gravity acting, it's still free fall. And the other mistake people make is when, so if there's a significant air resistance, then by definition it's not free fall because it's not free. In addition to gravity, you have to worry about other forces like air resistance. So once you have to start having to account for other forces other than gravity, then it's not free fall.